seen in a previous class, particularly if you took an AMP with Dr. Barlow. So sliding filament theory is our best guess at how muscle contraction works. It's pretty old now. The main idea is there's some little tweaking to it as we found out a bit more, but generally it hasn't changed very much. So hopefully we're right and this is how it happens. Okay. So the actin and myosin, remember the actin is the thinner protein filament, the myosin is the fatter one that has the little globular heads poking out there. And they slide across each other, which produces force. Right? So the actual protein filament doesn't change length, but remember that the actin is attached at one end to the Z line, and so as they slide across each other, the sarcomere does shorten. And then the muscle fiber is like a row of sarcomeres, so as they're all shortening, the muscle fiber shortens. Right? The number of bridges, cross bridges, or actin-myosin complexes that are formed at any one time dictates the amount of force that that muscle can produce. Right, so we have a step-by-step list. I prefer the picture, personally. But we'll go through the steps and then I'll show you the picture. Ignore step 3. Right? We don't need that much information. Right? So the first thing that happens is that we get a signal from the central nervous system at the neuromuscular junction, which we will talk about more when we get to chapter 5. Right? The neuromuscular junction is the point at which the nerve ending meets the sarcolemma of the muscle and transmits the signal. Right? The signal, the impulse, the electricity, runs across the surface of the muscle, and when you look at the surface of the muscle, there are little holes. They're like manholes. Right? And the hole leads into the T-tubule. The T-tubule runs through the fiber, happens to lie quite close to where the sarcoplasmic reticulum is situated. And so, because that signal is in the T-tubule, it's able to stimulate the sarcoplasmic reticulum to release calcium. So we don't just use calcium to keep our bones strong, we use calcium for muscle contraction as well. Right? If you remember back to that rather unpleasant picture of the young lady with anorexia, one of the reasons that people who are anorexic are at such high risk for osteoporosis is because if they're not feeding their body calcium, it's way more important to the body that it can contract muscles than it is to have strong bones. So it will leach calcium out of the bone in order to function, to have muscle contraction function. Right? So the calcium binds to the troponin, ignore the C subunit. Remember on Monday I said we're just going to go with calcium, with troponin. And that binding causes a little bit of a wiggle in the actin molecule. And it moves the tropomyosin strand slightly away from the actin, and it uncovers the site on the actin that is the attractor site for the myosin head. So once that site is uncovered, the myosin head can bind, right, and we get the cross bridge. And then remember the myosin head has that pivot joint, right? So the myosin head flicks, and because it's now attached to the actin, as it flicks, it pulls the actin along with it. Right? So when the muscle is at rest, when there is no signal from the central nervous system, we're not releasing calcium. Calcium isn't binding to troponin and causing the shift in the molecule. And so the actin site is covered up by the tropomyosin, and we can't get a cross bridge formed, and therefore we don't have contraction.
Let's do it on the picture, it's a bit easier, I think.
I'm of the opinion that pictures are always easier. Okay, so. All right. So, this is a schematic of a motor nerve. Okay. So the motor nerve is carrying the signal from the central nervous system to the muscle to tell it to contract. And it synapses with the surface of the muscle fiber, and the signal crosses to the muscle fiber and runs along the surface. Then it kind of falls down the manhole, right, down the T-tubule, into the middle of the cell, and it stimulates the sarcoplasmic reticulum to release calcium. Calcium binds to the troponin. That causes a shift in the shape of the molecule, which moves the tropomyosin off of the actin binding site and allows the head of the myosin to attach. Then the head flicks and drags the actin with it. Right? And the actin is attached at each end, one end on one end of the sarcomere and then another piece of actin on the other end, and so they both get pulled closer together. Okay, want me to do it again? Helps sometimes to hear it several times. Want it again?
Yeah, you do it one more time.
One more time? All right. All right, so the motor nerve is bringing a signal from the central nervous system to tell the muscle to contract. Right? That signal crosses the synapse and runs along the surface of the muscle fiber, down the T-tubule, and just because of where the T-tubule is placed in relation to the sarcoplasmic reticulum, the kind of network of ribbing around the muscle fiber, it stimulates the SR to release calcium ions. The calcium ions float across the cell and attach to the troponin, which is one of the 3 protein molecules that make up the actin filament. When the calcium attaches, then we see a little shift, kind of a wiggle in the molecule, and the tropomyosin, the long, in this diagram, green strand, moves slightly and uncovers the actin binding site. Then lying next to the actin is a filament of myosin, and so now there's a myosin head that's close to the actin binding site. Now the site is available, it can attach, and once it attaches, it flicks and drags the actin with it. time there's a signal coming down this nerve, this just keeps occurring, right? It attaches, it flicks, it unattaches, it cycles around, it attaches to the next one, it flicks, it cycles around, it attaches to the next one. And if you remember the diagram from Monday, there's lots and lots and lots of these heads. It's not like there's just one on the filament. Yeah. I can't give you an answer, but I mean, just doing that, that's happening thousands of times. Yeah. Right. So it's going to keep ratcheting and moving around, right, until the signal stops coming down the nerve. When the signal stops coming down the nerve, the calcium gets pumped back into the sarcoplasmic reticulum. So now there's no longer calcium available to attach to the troponin. The molecule shifts back to its original shape, and the active site is covered up by the tropomyosin. So that stops the contraction, but remember we said that I can't lengthen a muscle. I can only shorten a muscle, all right? So once the contraction is turned off, then the muscle gets lengthened either because the antagonistic muscle is contracting and pulling the arm down, or gravity is pulling the arm down and pulling the muscle back out to its resting length. So they have another set of they have another set of diagrams that tries to show you this in close detail. All right, here's unattached because there's no calcium. Here there's calcium attached, and so the molecule has shifted, and now the myosin head can stick to the binding site. Okay. Then it's flipping, and so we see movement in that direction. So they're quite a fancy set of diagrams. I have to say that this one, for me, is starting to get too complicated. I don't find this very helpful personally. You might, but I do have a video that I'm going to show you which I do like. All right. What we have to pay attention to is, remember that we've spent a lot of time looking at system 1, system 2, system 3 in order to make ATP for muscle contraction. Right? Where the ATP comes in is around the myosin head. Remember, the myosin is made of ATPase. That head, that globular head, is ATPase. So that whole head is made of enzyme to break down ATP, or to facilitate breaking down ATP. All right? So ATP has to be available for the head to let go and be able to recycle around. And then it releases energy, it breaks down the ATP, and the energy is released to cock it back to start again. Yes?
So when it comes to type 1 and type 2 muscles, do you know on a molecular level like how they differ? Like, does anything change?
The myosin ATPase has different isoforms. So the type of myosin ATPase in a type 2 is slightly different to the type in a type 1. And it works a little faster. That's as much as I know.
Are there,
Yes?
are there the same number of like heads for each type, or is like one type have more head than two?
I haven't heard that. I would imagine there's probably the same number, but maybe not so many of them attach at one time in a type 1. But that's a good question. I have never thought of that. I'll see if I can find that out for Friday. Okay, so let me show you. Let's pull this up. The volume on this computer has been a little kaplooey, so I don't know if I can get it any louder.
You use muscles every day to do activities. This woman is using muscles to breathe, circulate blood, and move her hand to take notes. Your cardiac and smooth muscle tissues are involuntary. You do not consciously control their actions. Skeletal muscle works under voluntary control. Skeletal muscles are composed of bundles of muscle fibers. Muscle fibers are long cylindrical cells containing several nuclei. Muscles will contract or relax when they receive signals from the nervous system. A neuromuscular junction is the site of the signal exchange. This is where the synaptic bulb of an axon terminal and muscle fiber connect. Muscle fibers are composed of many myofibrils. A myofibril contains contractile units called sarcomeres. Sarcomeres run adjacent to one another down the length of the myofibril. Each sarcomere consists of alternating thick and thin protein filaments, giving skeletal muscle its striated appearance. The muscle contracts when these filaments slide past each other. The thick filaments are myosin, which are anchored at the center of the sarcomere, called the M line. The thin filaments are composed of the protein actin, which are anchored to the Z lines on the outer edges of the sarcomere. Because the actin filaments are anchored to the Z lines, the sarcomere shortens from both sides when actin filaments slide along the myosin filaments. Although the action between the filaments is described as sliding, the myosin filament actually pulls the actin along its length. The crossed ridges of the myosin filaments attach to the actin filaments and exert force on them to move. This action is known as the sliding filament mechanism of muscle contraction. In this model, the sarcomeres shorten without the thick or thin filaments changing in length. A contraction begins when the bound ATP is hydrolyzed to ADP and inorganic phosphate. This causes the myosin head to extend and can attach to a binding site on actin, forming a cross bridge. An action called the power stroke is triggered, allowing myosin to pull the actin filament toward the M line, thereby shortening the sarcomere. ADP and inorganic phosphate are released during the power stroke. The myosin remains attached to actin until a new molecule of ATP binds, freeing the myosin to either go through another cycle of binding and more contraction, or remain unattached to allow the muscle to relax. Muscle contractions are controlled by the actions of calcium. The thin actin filaments are associated with regulatory proteins called troponin and tropomyosin. When a muscle is relaxed, tropomyosin blocks the cross-bridge binding sites on actin. When calcium ion levels are high enough and ATP is present, calcium ions bind to the troponin, which displaces tropomyosin, exposing the myosin binding sites on actin. This allows myosin to attach to a binding site on actin, forming a cross bridge. Calcium ions are stored in the sarcoplasmic reticulum and are released in response to signals from the nervous system to contract. Neurotransmitter molecules are released from a neuron and bind to receptors, which depolarizes the membrane of the muscle fiber.
Don't worry too
The
much about
electrical
that detail,
impulse
because
travels
that's the
down the
next chapter.
T-tubules and opens calcium stores. Calcium ions flow to the myofibrils, where they trigger a muscle contraction. As the actin and myosin slide along each other, the entire sarcomere shortens as the Z lines draw closer to the M line. As the sarcomeres in myofibrils contract, the entire muscle fiber will shorten. When muscle fibers contract in unison, a muscle can produce enough force to move the body, allowing you to take notes.
Ta-da!
Romeo and Juliet, Paladin, Paris,
Uh-oh.
Tristan, Isolde. These games star constantly.
No, shush, go away.
Goodness, goodness. So does the animation help? I find that really useful, doing it verbally. There is a very nice summary, if you like the written summary, on page 92. There's a box applying research on muscular contraction, and they have it set out very nicely step by step for contraction and for relaxation. So if you like the kind of bullet point approach, that's a good way to do it. Otherwise, the picture and the animation are good. There might be some other animations at the website for the textbook on the study guide. I know they have a link that I can see that says animations. I just haven't looked at what they've got there. Okay, but you can always, that's just on YouTube, that one. You can just YouTube sliding filament theory, and there's all kinds of, some are simple and some get a bit complicated, so make sure that you keep it simple. Right? So, good on sliding filament theory? Okay, so we're going to move on to proprioception. And this is one of the topics where you really see the interaction between different sports science disciplines, because proprioception is involved with the sensory information that your body is receiving, that it sends to the brain, that your brain then converts into pictures or into tweaking your motor skill because the information it's getting says it needs to change something. And so it links very closely then with motor control. And so it's interesting how they all overlap with each other, I think. So we've got this constant flow of information from many different sensory organs, right? I have pressure organs in the base of my feet that tell my brain whether I'm on balance or not. I've got my vestibular system in my inner ear that also gives my brain information about whether I'm upright, whether I'm spinning around. Right? So proprioception is talking about how does my body know where I am in the space that I'm inhabiting. So when we're looking at the muscular system, we have two specific proprioceptors, two sense organs that we're interested in because of the amount of information that they send to the brain or to the central nervous system. Right? So one is located actually in the muscle tissue, and one is located at the junction as the epimysium, the endomysium are all blending together into the tendon. Okay. And that information from those organs then is sent to the spinal column, and it can loop around in the spinal column as an involuntary response, so like a reflex action, or it can synapse with a nerve, a sensory nerve that is going to carry information up to the brain, and so the brain gets information about what's happening in the muscle tissue. So sometimes that information becomes conscious and we're aware of what we're being told, and a lot of it stays at the subconscious level. But there is a learning effect that involves these proprioceptors, right? So when I am learning a motor skill, one of the things that I have to be able to do is judge when to turn on force and when to turn it off, how much force to turn on at any one time, right? Can I adjust the force production if I'm not getting the outcome that I want on the skill, right? So I have to be able to repeat. If I want to be able to do the skill again, I've got to be able to repeat the pattern of turning the muscle fibers on that worked, right? So there has to be a learning curve going on there, right? And that's part of what's happening when we practice skills and we improve at skills, is the brain learning to turn on this muscle a little bit more, turn on another muscle, maybe, ooh, that was too much force, I need to turn it down a little bit next time, okay? When you're a movement person and you're good at something, you know if it feels right, right? One of the things that we aim for when we're teaching motor skills is to get the individual to the point where they know that they did something wrong without me telling them that they did something wrong, right? Well, the way they know that they did something wrong is from sensory information that doesn't match what should have happened. So, the first one of our sensory organs is the muscle spindle. Okay. And the muscle spindle almost looks like another muscle fiber. It's long and thin, and it lies in parallel to the muscle cells, to the muscle fibers. And it attaches at each end to the tendon. Well, it attaches to the endomysium and the perimysium. So it also has some nerve endings associated with it, right? There are actually two afferent, so sensory nerves are afferent, motor nerves are efferent. Okay? So it has a nerve that's wrapped around the spindle, and when I stretch the muscle, when I pull on the muscle, because of the way the spindle lies and is attached, I also pull on the spindle, which, if that pull is strong enough and fast enough, will stimulate information to be sent to the spinal column via the sensory nerve. Okay. Then, at the spinal column, the sensory nerve synapses, and we get the spinal column, there's a motor nerve that comes back and tells the muscle to relax. No, wrong way around, tighten. Sorry. Yes, tighten. Ooh, brain fog. So when this occurs as a reflex, we call it a stretch reflex. When we're in sport, we are very thankful for stretch reflexes, because even though we manage to twist our ankle and do all kinds of things on a regular basis, without a stretch reflex, it would happen way more often, right? So if I slightly turn my ankle, most of the time I don't keep going and end up spraining or breaking my ankle, because as I stretch the muscles on the outside of the ankle, they initiate a contraction that pulls the ankle back in line. Okay. So the faster and the harder the change in length, the stretch on the muscle, the stronger the response back to contract the muscle to try to protect it. So one of the functions of a muscle spindle is to protect that muscle from being torn. Right? Another job that it has is to send information to the brain about what is happening in the muscle when it initiates this move. Right? So I stretch the muscle, a signal gets sent to the spinal column, another signal comes back to the muscle and tells the muscle to contract. When the signal goes to the spinal column, it synapses multiple times. So some of that information goes to the brain and lets the brain know that the muscle was in danger of overstretching, and some of it will loop around within a reflex in order to rescue the muscle. So stretch reflex is another way of adding force into a powerful jump. Right? We talked about the fact that we have the rubber coil reflex within the endo and epimysium and perimysium, but we also have this stretch reflex. So if I do a pre-stretch in a really skilled action, the pre-stretch will initiate contraction. Right? So now I've got several different mechanisms that are adding force to a power event. Right? If you watch, I'll have to go with gymnastics because that's the one I know the best. If you watch the gymnasts on doing giant circles on bars, just before they hit the bottom, they'll drop their heels back and push the hip forward a little bit. That puts a stretch on the hip flexor so that then they can whack up the front to get over the top of the bar. So we use this all the time in skilled action. We just aren't always aware that we're utilizing it. Uh-oh. Sorry, distance people, I'm throwing you on the floor. This thing keeps coming out of its little... They shouldn't give me gadgets. It's really not safe. All right. So with training, not only do we see some adaptation in the muscle fiber, but we also see a little bit of adaptation in the actual muscle spindles, right? So they adjust their length, they get a little bit longer. That makes them more sensitive, which gives them a little more control then in a really skilled action. So it's another adaptation that we see that's going to benefit the action that we're doing. Sensory organ number 2 is the Golgi tendon organ, or GTO. And the spindle responds to stretch, change in length. The GTO is responsible for responding to tension in the muscle and the tendon. So that's being developed by the force that's being produced within the muscle. Right? because that tendon is responsible, remember, for transmitting the force from the muscle to the bone. Any force that's being picked up by the GTO is being created by the muscle. So if there's a large force on the tendon, there's lots of tension being created within the muscle and the tendon, the GTO will send a signal to the spinal column saying too much tension, and we get a signal back to the muscle that says relax, chill out, turn off some of those motor units, let's take some of the tension out here, otherwise this muscle is going to blow up. Right? So again, it has a protective function, because if there's too much force in the muscle, then it can rupture the tendon, or if the tendon doesn't give way, it can smash the bone. Right? So I've had 2 Achilles tendon ruptures, so apparently my GTOs were functioning very well at the time. There's a story several years ago about a baseball player. I can't remember his name, you might know Blake. He pitched a ball, and as he released the ball, his arm broke because he had generated so much force that the arm gave way. I suspect he was taking something he shouldn't have been taking that might have led to a little bit of a problem there, but it does happen. So let's think about what this means then. If we're weight training, then I'm deliberately trying to generate a large force in the muscles in order to push the weight. Right? So if my GTOs are telling my muscles to relax halfway through my bench press and I drop the bar on my face, I'm not going to be too happy about that. Right? So one of the reasons we can't lift very much early on is not just that the muscles can't generate it, but it's also that the GTOs are turning the force down in the muscle. So again, one of the training adaptations that we see when we do a lot of lifting is that the GTOs learn to inhibit, to turn down their response to a given force. Which is pretty cool, because otherwise we wouldn't be able to do 1 RMs, because halfway through the muscles would go okay? So they have a protective role, they inhibit the action of the muscle, but there is fatigue in the proprioceptive system, right? So probably with my tendon rupture was due to fatigue in the system, and the signal didn't work fast enough for the muscle to relax and not explode, right? It is something to pay attention to when you're training really hard, when you're in that high intensity period of your training and you're working really, really hard. We'll talk later in the semester about how important it is to build rest periods into your week, right? But one of the reasons we need rest periods is if this system is not working properly, then that little twist on your ankle that doesn't turn into a sprain turns into a 3rd-degree sprain. And then you don't get to walk on it for 3-4 weeks. Right? So we do have to be aware of the fact that there's physiological fatigue in a system we have no conscious awareness of. I mean, I wouldn't know if my muscle spindles are tired, right? How would I know that? So it is an important idea to kind of stick away at the back of your mind. When we talk about having rest days, it's not just resting your brain and resting your muscles, it's resting a system you are not really in control of as well. So that schematic is a little bit simple and easy to follow. Here's my muscle spindle. Here's my sensory nerve coming into the spinal column, synapses to the motor nerve, and tells the muscle to tighten. We would have the same thing here, right? There would be a sensory nerve coming in, sends a signal back to relax. Yes?
I was told that the golden tendon also plays a role in stretching, and it lets you release.
Yes, when we look at PNF stretching in particular, but when we look at stretching, both of them play a role. The muscle spindle plays a role in why we shouldn't bounce, and the Golgi tendon organ plays a role in how we can get the stretch to go a little bit further if we use it carefully. Yeah. Right. This little interneuron between the sensory neuron and the motor nerve. Might be a mistake on my language. Remind me to come back to that when we talk about interneurons, because I'm pretty sure that a stretch reflex doesn't have an interneuron. It's a bit complicated for my poor brain. I'm going to have to look it up and remind myself. That's not one of my memory pieces. All right. So, on Friday, we'll look at different actions that occur within the muscle. Okay, and we'll look at adaptation in the system to training.